Something invisible is tearing through space at a speed that defies comprehension. A supermassive black hole 10 million times more massive than our Sun is rocketing through space at a staggering 2.2 million miles per hour, which equals 1,000 kilometers per second. That velocity makes this one of the fastest moving bodies ever detected, rocketing through its home galaxy at 3,000 times the speed of sound at sea level here on Earth. Fast enough to travel from Earth to the Moon in 14 minutes. Fast enough to cross the entire diameter of our galaxy in less than 50,000 years. But here's the truly strange part. This cosmic monster is not destroying everything in its path. It's creating something. The black hole is pushing forward a literal galaxy-sized bow shock of matter in front of it, while simultaneously dragging a 200,000 light-year-long tail behind it, within which gas is accumulating and triggering star formation. Think about that for a moment. A black hole, an object we associate with destruction and consumption, is leaving a trail of newborn stars in its wake. Stars that would never have existed if this cosmic leviathan had stayed where it belonged. This is not theoretical speculation. This is not a computer simulation. The black hole, now officially named RBH1, was first reported in 2023 at a light travel time of 7.5 billion years, screaming across space, with an enormous bow shock in front of it, and a trail of star formation extending for 200,000 light-years behind it. The confirmation came from the James Webb Space Telescope in December of 2025, when astronomers led by Peter Van Dokkum of Yale University used the telescope's near-infrared spectrograph instrument to map the velocity distribution across the bow shock. What they found validated predictions that had existed purely in theory for 50 years. Black hole escapes lived purely in the realm of theory until now. Astronomers had long suspected that under the right conditions, a supermassive black hole could be violently ejected from its host galaxy. The physics made sense. The mathematics checked out. Computer simulations showed it was possible. But seeing it happen in the real universe is something entirely different. This is the first confirmed runaway supermassive black hole ever observed. The first time we've watched one of these cosmic giants break free from its gravitational prison and tear through space, leaving evidence of its passage written in stars. The implications stretch far beyond this single object. If one black hole can escape, others must have as well. The universe may be populated by invisible wanderers, dark titans moving through the void between galaxies, undetected and uncounted. The story of how RBH1 came to be hurtling through space begins billions of years ago with a cosmic collision. Two galaxies, each harboring a supermassive black hole at its center, began their slow gravitational dance toward merger. Galaxy collisions unfold over hundreds of millions of years. Stars rarely collide directly because the distances between them are so vast. But galaxies themselves, with their dark matter halos and gas clouds, interact through gravity's inexorable pull. As the two galaxies merged, their supermassive black holes spiraled inward toward the center of the newly formed galaxy. Both scenarios begin when two galaxies collide and begin to merge, each bringing to the cosmic smash its own supermassive black hole. Both mechanisms are initiated when the supermassive black holes reach the center of the newly formed galaxy. Here's where the story becomes extraordinary. When two supermassive black holes merge, they don't simply combine smoothly into a larger black hole. The process releases gravitational waves, ripples in space-time itself, that carry energy away from the system. But here's the critical detail. If the merger is not perfectly symmetrical, if one black hole is spinning at a different rate or oriented at a different angle, the gravitational waves are emitted more strongly in one direction than another. As they moosh together to form one supermassive black hole, the asymmetrical release of gravitational energy would have imparted a recoil kick that sent the newly formed black hole flying. It's like firing a gun. The bullet goes one way, the gun recoils the other. In this case, the bullet is gravitational waves carrying energy away in a preferred direction, and the gun is a supermassive black hole weighing millions of times more than our Sun. The forces involved are staggering. The forces that are needed to dislodge such a massive black hole from its home are enormous. To accelerate something with the mass of 10 million suns to a velocity of nearly 1,000 kilometers per second requires an energy release equivalent to a significant fraction of the black hole's rest mass energy converted into gravitational waves. This is not a gentle process. This is one of the most violent events that can occur in the universe, exceeded only by the collision itself. The recoil velocity can reach speeds of several thousand kilometers per second in extreme cases. In the case of RBH1, the velocity was measured at 954 kilometers per second, plus or minus about 120 kilometers per second. Watch what happens when a supermassive black hole is ejected at this velocity. It doesn't simply drift away quietly into intergalactic space. It plows through the circumgalactic medium, the tenuous gas and dust that surrounds its host galaxy. The passage of the black hole has a dramatic impact on its surroundings. It drives a shock wave in the gas that is moving through, and it is this shock wave and the wake of the shock wave behind the black hole that we see. The circumgalactic medium is incredibly diffuse, with densities far lower than the best vacuum we can create on Earth. But when something as massive as a supermassive black hole passes through it at nearly 1,000 kilometers per second, even this tenuous gas responds. The black hole compresses the gas in front of it, creating a supersonic bow shock. Think of a boat moving through water. The bow of the ship pushes water aside, creating a V-shaped wake that spreads out behind it. Or think of a supersonic aircraft breaking the sound barrier, creating a shock cone as it compresses the air in front of it. The same physics applies on a cosmic scale. As the bow of a ship moves through water, it compresses the water in front of it, which then flows around the bow and rejoins in a thinner line behind it. On a cosmic scale, gravity, not the collision of water particles, forms the same pattern. The black hole's gravity and velocity compress the circumgalactic medium gas ahead of it into a dense shock front. Behind the shock front, in the wake of the black hole, the compressed gas cools and begins to collapse under its own gravity. This is where star formation begins. Gas must be compressed before it can collapse to form stars. Normally, this compression occurs in giant molecular clouds within galaxies, triggered by supernova shock waves or spiral density waves. But the wake of a runaway supermassive black hole provides an entirely different mechanism. In the wake, many new stars have formed from the shocked gas, about 100 million times the mass of the Sun. This mode of star formation was unknown before, and it leads to a trail of stars far away from the galaxy, seemingly formed in empty space. The trail stretches for 200,000 light-years, twice the diameter of the Milky Way galaxy. Stars that should not exist, formed in a region of space where stars normally never form, created by the passage of an object that normally destroys everything near it. The paradox is striking. Black holes are engines of destruction, cosmic monsters that devour anything crossing their event horizon. Yet RBH1 is moving too fast to consume the gas it encounters. The black hole is streaking too fast to take time for a snack. It cannot capture and accrete the gas because its velocity carries it past before gravitational capture can occur. Instead, it simply compresses the gas and moves on, leaving behind the raw material for star formation. The result is a stellar nursery 200,000 light-years long, a cosmic breadcrumb trail that points back to the black hole's galaxy of origin. The trail must have lots of new stars, given that it is almost half as bright as the host galaxy it is linked to. The discovery itself was serendipitous, one of those happy accidents that occasionally transform our understanding of the universe. Yale astronomer Peter van Dokkum was looking through Hubble Space Telescope images and noticed a suspected blemish that looked like a scratch on photographic film. For Hubble's electronic cameras, cosmic rays skimming along the detector looked like scratches. Most astronomers would have dismissed it as an imaging artifact, a glitch in the detector, something to be ignored. Van Dokkum looked closer. The curious linear feature was so unusual it was first dismissed as an imaging artifact from Hubble's cameras. But it appeared in multiple images taken through different filters at different times. Cosmic ray hits are random and transient. This feature was real. Follow-up spectroscopy using the Keck Observatory in Hawaii revealed the true nature of the streak. Keck LRIS spectra show that the ratio of doubly ionized oxygen to hydrogen beta varies from roughly 1 to roughly 10 along the feature, indicating a mixture of star formation and fast shocks. The spectrum showed emission lines characteristic of both star-forming regions and shocked gas. The colors along the feature varied in a systematic way. The stellar continuum colors vary along the feature and are well fit by a simple model that has a monotonically increasing age with distance from the tip. Stars near the tip of the feature, closest to the black hole, are youngest. Stars farther back toward the galaxy are progressively older. This is exactly what you would expect if a moving object is continuously triggering star formation along its path. The newest stars mark its current position, while older stars mark where it was in the past. But spectroscopy from ground-based telescopes could not provide the definitive confirmation. That required the infrared sensitivity and spatial resolution of the James Webb Space Telescope. In December 2025, JWST turned its near-infrared spectrograph instrument toward RBH1. The JWST data show a sharp kinematic discontinuity at the tip, with a radial velocity change of approximately 600 kilometers per second across 0.1 arc seconds, which equals 1 kiloparsec. This is the smoking gun, the unmistakable signature of a supersonic shock front. The velocity shifts measured by JWST are precisely what theory predicts for a supermassive black hole, moving through the circumgalactic medium at nearly 1,000 kilometers per second. The geometry of the system adds another layer of complexity. The black hole is not moving directly toward us or away from us. The black hole has an inclination of 29 degrees, plus or minus about 5 degrees. This means we're viewing the system at an angle, with the bow shock tilted toward us and the trailing wake tilted away. This orientation allowed astronomers to measure Doppler shifts in the gas at the shock front, providing a direct measurement of the black hole's velocity. The gas in the bow shock is blue-shifted, compressed, and heated as the black hole plows through it. Farther back along the wake, the gas shows progressively smaller velocities as it mixes with the surrounding circumgalactic medium. The previously puzzling kinematics along the linear feature, with the observed radial velocity decreasing from approximately 300 kilometers per second near the tip to approximately 100 kilometers per second closer to the former host galaxy, are naturally explained as gradual downstream mixing of shocked gas with the circumgalactic medium through turbulent entrainment. Think about the scales involved. 200,000 light-years. Light traveling at 300,000 kilometers per second takes 200,000 years to traverse the length of this star-forming wake. The stars at the far end of the wake, nearest to the galaxy, were forming when the universe was roughly 200,000 years younger than it was when stars near the black hole began forming. But remember, we're looking at light that has traveled 7.5 billion years to reach us. The Hubble image captures a moment in time when the universe was roughly half its current age of 13.8 billion years. We're seeing this system as it appeared when the universe was approximately half its current age. The black hole ejection happened 7.5 billion years ago, plus the time since ejection, which astronomers estimate at roughly 40 million years based on the ages of stars in the wake. This raises an uncomfortable question. How many other runaway supermassive black holes are out there, invisible and undetected? RBH1 was discovered only because it happens to be moving through a region with enough gas to trigger star formation, and because we happen to be looking at the right patch of sky at the right time with the right telescope. Simulations also suggest that there should be quite a large number of rogue supermassive black holes out there, invisibly lurking in the darkness of intergalactic space. Most ejected black holes would be moving through regions with far less gas, leaving no visible trail. Or they might be moving through intergalactic voids where the gas density is so low that even a supersonic passage leaves no detectable signature. These invisible wanderers could be everywhere, undetected dark masses moving through the space between galaxies. Galaxy mergers are common in the universe. Mergers between galaxies are common, occurring multiple times over the lifetime of a single galaxy. Most large galaxies, including our own Milky Way, have undergone multiple mergers throughout their history. Each merger brings together the supermassive black holes from both galaxies. In many cases, these black holes merge successfully, combining into a single, more massive black hole. But in some fraction of cases, the merger produces a recoil kick violent enough to eject the newly formed black hole from the galaxy entirely. Computer simulations suggest this happens in a significant percentage of mergers, depending on the masses and spins of the merging black holes. If even a few percent of galaxy mergers result in black hole ejections, the universe should contain millions or billions of runaway supermassive black holes. The implications extend to our own galaxy. The Milky Way is currently on a collision course with the Andromeda Galaxy. The two galaxies will begin their merger in approximately 4 billion years. Both galaxies harbor supermassive black holes at their centers. The Milky Way's central black hole, Sagittarius A star, has a mass of approximately 4 million solar masses. Andromeda's central black hole is larger, perhaps 100 million solar masses or more. When these two black holes eventually merge, roughly 6 to 7 billion years from now, will the resulting black hole be ejected through gravitational recoil? The answer depends on the spins and orbital parameters of the merging black holes, which cannot be predicted with certainty. But it's possible. Our galaxy's central supermassive black hole could, in the distant future, be flung out into intergalactic space, leaving the merged Milky Way Andromeda Galaxy without a central black hole. What happens to a galaxy that loses its central supermassive black hole? Surprisingly, not much in the short term. That would lead to a galaxy lacking a supermassive black hole at its center, which Van Dockum said is unlikely to impact said galaxy very much. The gravitational influence of the supermassive black hole extends only to the innermost regions of the galaxy, typically a few hundred light-years from the center. The vast majority of stars in the galaxy orbit in response to the gravity of all the other stars and the dark matter halo, not the central black hole. Remove the black hole and most stars would continue in their orbits largely unchanged. The galaxy would lack an active galactic nucleus, the bright accretion disk that forms when the black hole feeds on surrounding gas. Over time, the central regions might restructure themselves, with stars gradually filling in the gravitational potential well left by the missing black hole. But these changes would unfold over billions of years. The more dramatic effects would occur if a runaway supermassive black hole encounters another galaxy. An encounter with another galaxy would be quite spectacular, mostly because of the huge galaxy-sized shockwave that precedes the black hole. When this shockwave encounters the dense gas of another galaxy, it would compress and shock that gas and likely form a lot of new stars. It would be quite the show. Imagine a 10 million solar mass black hole moving at 1,000 kilometers per second, plowing through the disk of a spiral galaxy. The bow shock would compress the galaxy's gas clouds, triggering an enormous burst of star formation. The passage might create visible structures in the galaxy, bright arcs or shells of young blue stars marking where the interloper passed through. Astronomers looking at such a galaxy millions of years later might puzzle over these unusual features, unaware that they were created by a cosmic hit-and-run. The physics of the bow shock deserves deeper examination. When the black hole moves through the circumgalactic medium faster than the speed of sound in that medium, it creates a shock discontinuity. The speed of sound in a gas depends on temperature and composition. In the hot, ionized circumgalactic medium, with temperatures of 1,000,000 degrees or more, the sound speed is roughly 200 to 300 kilometers per second. RBH1 is moving at 954 kilometers per second, roughly 3 times the sound speed, making it a strongly supersonic object. At the shock front, gas moving at hundreds of kilometers per second relative to the black hole is suddenly decelerated to much lower velocities. This deceleration occurs over a very short distance, roughly 1 kiloparsec according to JWST measurements. The kinetic energy of the gas is converted into heat and turbulence. Temperatures behind the shock can reach tens of millions of degrees. The shock also compresses the gas, increasing its density by factors of several. This compression is crucial for star formation. Star formation requires cold, dense gas. Hot, diffuse gas cannot collapse to form stars because thermal pressure counteracts gravitational attraction. But behind the shock front, the compressed gas begins to cool. Cooling occurs through radiation, with hot gas emitting photons that carry energy away. The time required for cooling depends on the density and temperature. In the wake of RBH1, conditions are just right for cooling to occur within a few million years. Once the gas cools sufficiently, local density enhancements begin to collapse under their own gravity. Protostars form, gather surrounding gas, and ignite fusion in their cores. The process repeats along the entire length of the wake, with the black hole continuously triggering new episodes of star formation as it moves through fresh gas. The stars formed in the wake have unusual properties. They're forming in isolation, far from any galaxy. Most stars form in clusters, born together from the same collapsing molecular cloud within a galaxy. The stars in RBH1's wake are forming in a long, narrow filament, stretched across 200,000 light-years of space. Theory and modeling show that the youngest stars formed in the wake should be younger than about 30 million years old. When the researchers measured their properties, they found that the 3 knots are within the age range laid out by models. The stellar population is dominated by young, massive, hot blue stars. These stars burn brightly but briefly, with lifetimes of only a few million to a few tens of millions of years. Over time, as the black hole moves farther away, the older stars in the wake will exhaust their fuel and explode as supernovae, enriching the circumgalactic medium with heavy elements. Eventually, billions of years in the future, the wake will fade as the bright, massive stars die out, leaving behind a trail of faint, red dwarf stars, stellar remnants, an enriched gas. The metallicity of the stars in the wake provides clues about the history of the host galaxy. Metallicity, in astronomical terms, refers to the abundance of elements heavier than hydrogen and helium. Stars form from gas clouds, and the gas retains a chemical memory of previous generations of stars that enriched it with heavy elements from supernovae. The 3 knots are within the range of metallicities and dust content predicted by models. The stars in RBH1's wake have metallicities consistent with forming from gas that was part of the host galaxy's circumgalactic medium. This confirms that the black hole is compressing and cooling gas that originally belonged to its host galaxy, rather than pristine intergalactic gas that has never been processed through stars. Could this phenomenon be something other than a runaway black hole? Astronomers considered alternative explanations. It could be a black hole jet rather than a rogue supermassive black hole. Under the right conditions, black hole jets can also shock gas in the circumgalactic medium and lead to star formation. There are 2 well-studied nearby examples of jets triggering star formation. Jets are collimated beams of particles and radiation ejected from the poles of an actively feeding black hole. These jets can extend for millions of light-years and interact with surrounding gas. However, several observations argue against the jet interpretation for RBH1. Jets typically fan out as they move away from their source, becoming wider with distance. RBH1's wake is narrowest at the tip, farthest from the galaxy, and widest near the galaxy. This is opposite to what jets do. Additionally, if the host galaxy ejected an SMBH, the galaxy should show signs of disruption. Supermassive black holes are extraordinarily massive, and that much mass can't move through a galaxy without shaping it. The team examined the galaxy that spawned the rogue SMBH and found that its morphology was disrupted. The host galaxy shows irregularities and distortions consistent with recent dynamical upheaval, exactly what you'd expect if a massive black hole was violently ejected from its center. The bright knot at the tip of the wake presents another puzzle. There is a remarkably bright knot of ionized oxygen at the outermost tip of the column. Researchers believe gas is probably being shocked and heated from the motion of the black hole hitting the gas, or it could be radiation from an accretion disk around the black hole. This bright knot is where the black hole itself resides, the leading edge of the system. The ionized oxygen emission is extraordinarily strong, suggesting extreme conditions at this location. The black hole may have a small accretion disk, despite moving too fast to capture most of the gas it encounters. Gas directly in its path, unable to move aside quickly enough, might be captured and form a thin disk around the black hole. Accretion onto this disk would release energy as radiation, ionizing the surrounding gas and producing the observed emission lines. Alternatively, the shock itself might be powerful enough to ionize the gas without any accretion. Distinguishing between these possibilities requires additional observations. The measurement techniques used to study RBH1 showcase the capabilities of modern astronomy. Hubble Space Telescope provided the initial discovery through optical imaging, revealing the streak's morphology and color. Ground-based spectroscopy from Keck Observatory measured emission line ratios and redshifts, confirming that the feature was associated with a distant galaxy at redshift 0.964. This redshift corresponds to a look-back time of approximately 7.5 billion years, meaning we're seeing the system as it appeared when the universe was roughly half its present age. The James Webb Space Telescope provided the crucial confirmation through near-infrared integral field spectroscopy. JWST's NIR-SPEC instrument captures spectra simultaneously across a 2-dimensional field, creating a 3-dimensional data cube with spatial positions in 2 dimensions and wavelength in the third. This allows astronomers to map the velocity of gas across the entire bow shock region, revealing the sharp kinematic discontinuity that confirms the supersonic shock interpretation. The Chandra X-ray Observatory could provide additional confirmation. If the black hole has an accretion disk, that disk should emit X-rays as hot gas spirals inward. X-ray observations could detect this emission and measure the black hole's mass more precisely. The accretion rate would be low, given the black hole's high velocity and the low gas density of the circumgalactic medium, but modern X-ray telescopes might be sensitive enough to detect it. Future observations with upcoming telescopes will search for additional examples of runaway black holes. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will survey large areas of sky with sensitivity comparable to Hubble. Machine learning algorithms could be trained to identify candidate runaway black hole wakes in Roman's imaging data, finding features too faint or too unusual for human astronomers to notice. The Vera C. Rubin Observatory, currently under construction in Chile, will survey the entire southern sky repeatedly, potentially discovering transient or variable features associated with runaway black holes. The theoretical framework for black hole ejections has evolved significantly since the 1970s. Early work by theorists explored the dynamics of binary supermassive black holes in merged galaxies. When two galaxies merge, their central black holes initially remain far apart, each orbiting within the merged galaxy's core. Over time, dynamical friction, the gravitational drag exerted by surrounding stars and dark matter, causes the black holes to spiral inward toward the center. Eventually, when the separation becomes sufficiently small, the two black holes form a bound binary system. This binary then shrinks further through continued interactions with surrounding stars, which extract energy and angular momentum from the binary orbit. As the orbital separation decreases, the black holes eventually enter the gravitational wave regime, where emission of gravitational radiation dominates the orbital evolution. The final coalescence occurs when the black holes merge, an event that releases an enormous burst of gravitational wave energy. The asymmetry of the merger determines the recoil velocity. If the two black holes have equal masses and their spins are aligned with the orbital angular momentum, the merger is symmetric and produces minimal recoil. But nature rarely produces such perfect symmetry. More typically, the black holes have unequal masses, their spins are misaligned with the orbit, and the spins point in different directions. These asymmetries cause the gravitational waves to be emitted preferentially in certain directions, like a searchlight rather than a symmetric beacon. The momentum carried away by the gravitational waves in the preferred direction must be balanced by the black hole recoiling in the opposite direction. This kick can reach speeds of up to 1,000 kilometers per second. In extreme cases with highly spinning black holes and optimal spin configurations, recoil velocities can exceed 3,000 kilometers per second. At such velocities, the black hole easily exceeds the escape velocity of any galaxy and is ejected into intergalactic space. An alternative scenario involves 3 black holes rather than 2. When a third galaxy merges with a system that already contains a binary black hole, the third black hole can disrupt the binary through gravitational interactions. The 3-body problem is chaotic, meaning small changes in initial conditions produce wildly different outcomes. In many cases, the lightest black hole is ejected at high velocity, while the 2 more massive black holes form a tighter binary. This slingshot scenario can produce even higher recoil velocities than binary mergers. The mysterious linear streak and its counterstreak are the shocked gas wakes left behind by ejected supermassive black holes. The counterstreak is fainter and shorter because it is created by the slower-moving binary, while the main linear feature is brighter and faster because it is created by the faster-moving third supermassive black hole. Observers have noted a fainter feature on the opposite side of RBH1's host galaxy, which could potentially be the wake of a binary black hole ejected in the opposite direction during a three-body interaction. However, this counter-feature is much fainter and less certain than the main wake. The long-term fate of RBH1 depends on its velocity relative to the escape velocity of the local cosmic environment. RBH1 is indeed rocketing through the very outer edges of its galaxy towards intergalactic space. The galaxy's escape velocity at the black hole's current location is likely several hundred kilometers per second, significantly less than the black hole's velocity of 954 kilometers per second. This means the black hole will continue moving outward, eventually leaving the galaxy entirely and entering intergalactic space. Once in intergalactic space, the black hole will continue moving through the cosmic web, passing through the filaments and voids that structure the large-scale distribution of matter in the universe. It may eventually encounter another galaxy, either passing through it or being captured if its velocity decreases sufficiently through dynamical friction. Or it may simply continue moving indefinitely, a dark wanderer in the space between galaxies. On cosmic timescales, the black hole's velocity will decrease gradually. Although intergalactic space is nearly empty, it's not perfectly empty. Interactions with dark matter particles, if dark matter has any interaction strength with baryonic matter beyond gravity, could gradually slow the black hole. Gravitational interactions with occasional gas clouds or galaxies it passes near will also extract energy from its motion. Over billions of years, perhaps tens or hundreds of billions of years, the black hole might slow enough to be captured by another galaxy. Or it might simply continue moving, its velocity decreased, but never reaching zero, until the universe reaches its ultimate fate, whatever that may be. The star-forming wake itself has a limited lifetime. Star formation requires gas, and the black hole is rapidly exhausting the gas supply along its path. The total stellar mass formed in the wake, roughly 100 million solar masses, is substantial but finite. The wake stretches for 200,000 light-years, implying a linear mass density of roughly 1 solar mass per 2 light-years. This is extraordinarily low compared to stellar densities in galaxy disks, where typical densities exceed 100 solar masses per cubic parsec. The stars in RBH1's wake will gradually disperse over time. They have random velocities imparted by the turbulent conditions of their formation. These velocities, typically several kilometers per second, will cause the stellar trail to spread and blur over hundreds of millions of years. Eventually, the once linear structure will become an amorphous cloud of stars in intergalactic space, unrecognizable as having originated from a runaway black hole wake. The metallicity evolution of intergalactic space may be significantly impacted by runaway black holes if they are common. Massive stars in the wakes will explode as supernovae within a few million to a few tens of millions of years after formation. These supernovae will enrich the intergalactic medium with heavy elements, seeding the void between galaxies with carbon, oxygen, silicon, iron, and other elements synthesized in stellar cores. If runaway black holes are common enough, this process could significantly contribute to the metal content of the intergalactic medium, affecting the properties of gas that later falls into galaxies during cosmic structure formation. The chemical fingerprints of runaway black hole passages might be detectable in future surveys of intergalactic gas, appearing as metal-enriched filaments or clouds in otherwise pristine gas. The detection of RBH1 opens a new observational window on galaxy evolution and supermassive black hole dynamics. For decades, astronomers have inferred the presence of supermassive black holes through their gravitational effects on surrounding stars, or through the radiation emitted by their accretion disks. But these methods only work for black holes that remain in galaxy centers. Ejected black holes moving through regions with little or no surrounding matter are essentially invisible to these techniques. The wake method provides a way to detect even quiescent black holes, as long as they're moving through regions with sufficient gas density to trigger observable star formation. This technique could reveal a previously hidden population of black holes, reshaping our understanding of how many supermassive black holes exist in the universe and where they reside. The statistical properties of the runaway black hole population remain uncertain. How many exist? What is the distribution of their masses and velocities? How far from their parent galaxies do they typically travel before slowing down or being captured by another galaxy? These questions cannot yet be answered with a sample size of 1, but future discoveries will begin to constrain the answers. If runaway black holes are rare with only 1 per 1,000 galaxies, they're an interesting curiosity but not a major factor in cosmic evolution. If they're common, with 1 per 10 or 1 per 100 galaxies, they could significantly impact galactic evolution, stripping galaxies of their central black holes and enriching intergalactic space with metals from the stars formed in their wakes. The impact on gravitational wave astronomy is profound. When two supermassive black holes merge, they emit gravitational waves that carry information about the masses, spins, and orbital parameters of the merging system. The final recoil velocity is directly related to these parameters, particularly the spins and their orientation relative to the orbital plane. By detecting runaway black holes and measuring their velocities, astronomers can constrain the properties of the mergers that produced them. This provides an independent check on gravitational wave observations. Future gravitational wave detectors, such as the Laser Interferometer Space Antenna, or LIDAR, will be sensitive to the frequency range of merging supermassive black holes. LISA will detect these mergers out to cosmological distances, potentially observing thousands of events over its mission lifetime. Correlating gravitational wave detections with optical or infrared observations of runaway black hole wakes could provide unprecedented insights into the merger process. The observational search for additional runaway black holes faces significant challenges. The wakes are faint, requiring deep imaging with large telescopes. They're also rare enough that large sky surveys are needed to find them. Machine learning offers a promising approach. Algorithms can be trained on the characteristics of RBH1's wake and then applied to large imaging datasets to identify similar features. The algorithm would look for linear features with specific color gradients, emission line ratios, and connections to host galaxies. False positives would be common, including cosmic ray artifacts, image defects, and linear structures produced by other astrophysical phenomena. But automated screening could flag candidates for follow-up spectroscopy, allowing efficient searches through vast archives of imaging data. The upcoming Legacy Survey of Space and Time from Rubin Observatory will image the entire southern sky repeatedly over 10 years, generating petabytes of data. This dataset will be ideal for machine learning searches for runaway black hole wakes. The implications for our understanding of supermassive black hole formation and growth are significant. Astronomers have long known that nearly all large galaxies contain supermassive black holes at their centers. It is commonly accepted that the center of nearly every galaxy contains a supermassive black hole. The reason for this assumption is the M-sigma relation, a tight relation between the mass of the hole in galaxies with secure detections and the velocity dispersion of the stars in the bulges of those galaxies. This correlation suggests to many astronomers a strong connection between the formation of the black hole and the galaxy itself. This correlation, known as the M-sigma relation, links the black hole mass to properties of the galaxy's bulge. The tightness of this relation suggests a deep physical connection, with the black hole and galaxy somehow regulating each other's growth. But if black holes can be ejected, this challenges simple models of co-evolution. A galaxy that loses its black hole breaks the M-sigma relation. The galaxy bulge remains, but the black hole is gone. Over time, if galaxy mergers and black hole ejections are common, the population of galaxies should include a significant fraction with missing or undermassive central black holes. Observational searches for galaxies lacking central supermassive black holes have produced tantalizing hints. Several galaxies appear to have unusually low central black hole masses, or no detectable black hole at all, given the properties of their bulges. These could be galaxies that have lost their black holes through ejection. Alternatively, they could be galaxies that never formed large black holes in the first place, or galaxies where the black hole is present, but not actively accreting and therefore difficult to detect. Distinguishing among these possibilities requires careful observations. The presence or absence of a dark mass concentration at the galaxy center can be measured through stellar kinematics, looking at the velocities and orbits of stars in the innermost regions. If stars show no evidence of a central mass concentration beyond the stellar mass itself, the black hole may truly be missing. Several candidate galaxies have been identified through this method, though none with definitive proof. The theoretical understanding of how black hole ejections affect galaxy evolution is still developing. Simulations can model the dynamical process of ejection, calculating recoil velocities and the trajectories of ejected black holes. But understanding the long-term consequences requires modeling galaxy evolution over billions of years, including gas inflows, star formation, supernova feedback, and repeated merger events. Do galaxies that lose their central black holes evolve differently from galaxies that retain them? The answer likely depends on the timing of the ejection. If the black hole is ejected early in the galaxy's history, before it has grown massive, the impact may be minimal. The galaxy continues forming stars and evolving much as it would have anyway. If the black hole is ejected after it has grown massive, having already influenced the galaxy through feedback from its accretion activity, the consequences could be more significant. The sudden removal of a massive central object could trigger dynamical instabilities in the galaxy's core, potentially affecting star formation rates or triggering bursts of nuclear star formation. The connection to active galactic nuclei is complex. Active galactic nuclei, or AGN, are supermassive black holes that are actively accreting gas, producing enormous luminosities that can outshine entire galaxies. AGN feedback, the energy and momentum injected into the surrounding gas by AGN activity, is thought to be crucial for regulating galaxy evolution. Simulations of galaxy formation require AGN feedback to prevent galaxies from forming too many stars too quickly. Without feedback, simulated galaxies grow too massive and too metal-rich compared to observed galaxies. But feedback requires the black hole to remain in the galaxy center, where it can interact with infalling gas. An ejected black hole cannot provide feedback. If a significant fraction of black holes are ejected during a galaxy's history, the cumulative effect of reduced feedback could alter the properties of the galaxy population. This could potentially help explain why observed galaxies are less massive than naive models predict, though many other mechanisms also contribute to this discrepancy. Return for a moment to the cosmic collision that created RBH1. Two galaxies merging 7.5 billion years ago, plus about 40 million years. They're supermassive black holes spiraling inward over hundreds of millions of years as dynamical friction drained orbital energy. the final plunge as gravitational waves dominated the orbital decay. The merger itself, a fraction of a second during which two black holes became one, releasing more energy in gravitational waves than all the stars in the observable universe emit in the same time period. The asymmetric emission of gravitational waves giving the newly formed black hole a kick of nearly 1,000 kilometers per second. The black hole beginning its journey outward through the galaxy, plowing through the disk, heating and shocking gas, leaving behind clusters of newly forming stars. Finally breaking free of the galaxy entirely, entering the circumgalactic medium where gas densities are lower but still sufficient to trigger the star formation we observe today in its wake. Think about what we're observing when we look at RBH1. Light left this system 7.5 billion years ago, when the universe was roughly half its current age. Earth did not exist yet. The Sun and Solar System would not form for another 3 billion years. The light traveled through expanding space for 7.5 billion years, eventually arriving at Earth where it entered Hubble's mirror, was focused onto detectors, and created the images that Peter van Dokkum noticed that day in the data. We're seeing this system not as it is now, but as it was incomprehensibly long ago. By now, in the system's reference frame, another 7.5 billion years have passed. The black hole has traveled an additional 7,000 light-years or more from where we see it. The stars in the wake have aged, the massive ones exploding as supernovae, the lower mass ones settling into stable main sequence burning. The host galaxy has continued evolving, possibly merging with other galaxies, forming new generations of stars. We'll never know what RBH1 looks like today. The light carrying that information won't reach Earth for another 7.5 billion years, long after the Sun has become a red giant and engulfed the inner planets. The philosophical implications ripple outward. We live in a universe where the most massive objects, black holes weighing millions or billions of times more than our Sun, anchored to galaxy centers by gravity's inexorable pull, can be violently ejected and sent flying through intergalactic space. We live in a universe where destruction creates creation, where a black hole's passage triggers the birth of stars that would never have existed otherwise. We live in a universe where invisible objects reveal themselves through the wakes they leave behind, where the absence of something, properly interpreted, tells us about the presence of something else. We live in a universe strange enough and violent enough and creative enough to produce phenomena like RBH1. And we live at a time in the universe's history when intelligent beings have developed the technology to detect and understand these phenomena. The search continues. Astronomers are now specifically looking for more examples of runaway black hole wakes in archival data and in new observations. Every deep image of a distant galaxy cluster or galaxy group is a potential discovery opportunity. The features are faint and easily overlooked, requiring careful examination of data that may have been taken for entirely different purposes. But they're out there. If RBH1 exists, others must also exist. The obvious next step for the team will be to search for more examples of runaway black holes. Finding more examples will allow statistical studies of the population. How common are they? What is the distribution of velocities? Do higher velocity black holes create more prominent wakes? Or do they move too fast for efficient star formation? Do wakes occur only in certain types of environments, or can they form in any galaxy with sufficient circumgalactic gas? These questions await answers. The technological requirements for finding more examples are substantial but achievable. Deep imaging requires large telescopes and long exposure times. Spectroscopic confirmation requires additional observations with different instruments. JWST time is precious and oversubscribed, allocated through competitive proposals. But the scientific payoff of finding more runaway black holes is high enough to justify the investment. Understanding the population of ejected black holes constrains models of galaxy mergers, supermassive black hole growth, gravitational wave emission, and galaxy evolution. These are fundamental questions in astrophysics, touching on the behavior of gravity in the strongest possible regimes, the formation of the largest structures in the universe, and the ultimate fate of galaxies over cosmic time. On a human scale, the story of RBH1 is humbling. We are creatures bound to the surface of a small planet orbiting an ordinary star in an unremarkable region of a typical galaxy. The events we're discussing, the collision of galaxies and the ejection of supermassive black holes, occurred when the universe was half its present age, in a galaxy so distant that light takes 7.5 billion years to traverse the distance. The energies involved, the conversion of mass energy into gravitational waves equivalent to millions of stars, are so far beyond our experience that we can barely grasp them, even intellectually. Yet we can understand them, we can observe them, we can construct telescopes sensitive enough to detect the faint trail of stars marking a black hole's passage. We can build mathematical models that predict the physics of supersonic shocks in the circumgalactic medium. We can use these models to interpret observations and confirm that what we're seeing matches what theory predicts. This is perhaps the most remarkable thing of all. Not that these phenomena exist, but that we can comprehend them. The detection of RBH1 represents decades of scientific progress coming together. Hubble Space Telescope, launched in 1990 and still operating after more than 3 decades, providing the initial discovery image. Ground-based observatories with decades of technological development in spectrographs and detectors, allowing detailed spectroscopic analysis. James Webb Space Telescope, decades in planning and construction, finally launched in 2021 and providing revolutionary infrared observations. Theoretical models developed by generations of astrophysicists, starting with early work in the 1970s predicting black hole ejections and continuing through modern supercomputer simulations of galaxy mergers and black hole dynamics. All of this coming together to confirm the existence of a phenomenon that was purely theoretical until a few years ago. If you find yourself wondering what happens next, you're not alone. The scientific community is wondering too. Will we find more examples quickly, or will RBH1 remain unique for years? Will we detect gravitational waves from the mergers that create these runaway black holes, allowing us to observe both the cause and the effect? Will we find runaway black holes in the process of colliding with other galaxies, triggering spectacular bursts of star formation? Will we discover that some galaxies thought to be normal actually lost their central black holes to ejections billions of years ago? These questions will drive research for decades to come. The universe continues to surprise us. Every time we think we understand the cosmic landscape, new observations reveal phenomena we hadn't anticipated. Runaway black holes creating trails of stars were predicted theoretically, but actually observing one transforms it from an abstract possibility to a concrete reality. Reality always exceeds our expectations, containing more detail, more complexity, more strangeness than our models anticipate. This is what makes astronomy endlessly fascinating. The universe is not obligated to conform to our expectations or our sense of what seems reasonable. It simply is, following the laws of physics wherever they lead, producing wonders like RBH1 along the way. Imagine standing on a planet in the host galaxy, looking up at the night sky a few million years after the ejection event. You might notice that the constellation patterns have shifted slightly, stars rearranged by the black hole's passage through the galaxy. You might see a faint linear streak in the sky, visible as a barely perceptible band of dim light, marking the trail of young stars forming in the black hole's wake. You wouldn't understand what you were seeing without telescopes and spectrographs and the accumulated knowledge of physics and astronomy. You might think it was a distant irregular galaxy edge-on, or a tidal stream of stars torn from a dwarf galaxy, or some other more mundane phenomenon. The truth that you're looking at the scar left by your galaxy's central black hole being violently ejected would be impossible to discern without sophisticated observations. But it would be there, night after night, a permanent reminder of the violent event that reshaped your galaxy's core. The stars forming in RBH1's wake are real places, or at least they were 7.5 billion years ago. Some of those stars undoubtedly have planets. The probability that at least some of the 100 million solar masses worth of stars formed planets is essentially 1. Those planets formed in an unusual environment, in a narrow filament of star-forming gas stretched across intergalactic space. A planet orbiting a star in RBH1's wake would have a bizarre sky. Few nearby stars compared to planets in galactic disks. The host galaxy visible as a distant oval of light. The opposite end of the stellar trail visible as a faint band stretching across the sky towards the galaxy. The rest of the sky dominated by darkness and the distant lights of other galaxies. An inhabitant of such a planet, if any exist, would have an unusual perspective on cosmic geography. They would know from looking at their sky that they lived not in a galaxy but in something else, something linear and isolated. They might wonder how their stellar neighborhood came to exist in such an unusual configuration. With sufficiently advanced astronomy, they might figure it out. The timescales involved challenge human intuition. 40 million years since ejection as estimated from the ages of stars in the wake. 7.5 billion years of light travel time. The universe was 6.3 billion years old when the light we're seeing left RBH1, compared to 13.8 billion years old now. The Milky Way existed then, though it was smaller and less structured than today, having undergone several mergers in the intervening time. The Sun and Earth would not exist for another 3 billion years. Dinosaurs would not appear on Earth for another 7.25 billion years after the ejection. Modern humans would not evolve for another 7.5 billion years minus 60,000 or so. Yet we can observe this event now, reach across the vast gulf of space and time with our telescopes and our physics, and understand what we're seeing. The story of RBH1 is still being written. New observations will refine the measurements, constraining the black hole's mass, velocity, and trajectory more precisely. Follow-up studies will search for X-ray emission from any accretion disk around the black hole. High-resolution imaging will resolve individual star-forming regions within the wake. Spectroscopic surveys will measure the metallicities of gas and stars along the wake, tracing the chemical enrichment history. Theoretical work will compare the observations to simulations, refining models of supersonic black hole motion through the circumgalactic medium. Other research teams will search for additional examples in different datasets, gradually building up a sample large enough for statistical analysis. Each new piece of information adds to our understanding of this remarkable phenomenon. One day, perhaps decades from now, textbooks will describe runaway supermassive black holes as a standard, well-understood component of galaxy evolution. Students will learn that a significant fraction of galaxies have lost their central black holes to ejections, and that the population of isolated black holes in intergalactic space rivals or exceeds the population in galaxy centers. They'll study the physics of bow shocks and star formation in black hole wakes, work through problem sets calculating expected recoil velocities from mergers with different spin configurations, and analyze data from surveys that have catalogued thousands of runaway black hole wakes. What seems extraordinary now will become routine, another piece of the cosmic puzzle that we've figured out and incorporated into our standard model of the universe. But for now, in this moment, RBH1 remains unique, a single confirmed example of a predicted phenomenon, a cosmic mystery we're only beginning to unravel. Think about the patience required for astronomy on these scales. Peter van Dokkum noticed something unusual in an image and decided to investigate rather than dismiss it. That simple decision led to follow-up spectroscopy, which led to JWST observations, which led to confirmation of the first runaway supermassive black hole. How many other anomalies are hiding in archived data, overlooked or dismissed as artifacts? How many discoveries are waiting for someone curious enough to investigate something that doesn't quite fit? The universe rewards attention and perseverance. It rewards people who notice the small details and wonder whether they might be important. It rewards people who, when they see a faint streak in an image that looks like a scratch on film, decide to look closer rather than assume it's nothing. The story returns to where it began, something invisible tearing through space at 2.2 million miles per hour. A black hole 10 million times the mass of the Sun, ejected from its galaxy through the most violent event possible, short of the Big Bang itself. Moving so fast that it cannot consume the gas it encounters, instead compressing it and leaving behind a trail of newborn stars 200,000 light-years long. Stars that will burn and explode and enrich their surroundings with heavy elements. Stars that may have planets. Stars that would never have existed if a cosmic collision billions of years ago hadn't sent a supermassive black hole careening through space. This is physics at its most extreme. This is gravity and dynamics and hydrodynamics pushed to the limits of what the universe allows. This is the cosmos showing us that reality is always stranger and more wonderful than we imagine. If this journey through cosmic violence and creation has resonated with you, know that the universe contains countless other marvels waiting to be discovered and understood. Every galaxy harbors secrets. Every patch of seemingly empty space might contain something extraordinary if we look closely enough with sensitive enough instruments. The detection of RBH1 reminds us that we live in a universe of wonders, a universe that rewards curiosity and careful observation, a universe where the impossible becomes possible and the invisible reveals itself through the traces it leaves behind. Consider the vastness of space and time, stretching before and after this moment, the countless phenomena unfolding across billions of light years, the intricate dance of matter and energy and space-time playing out according to laws we're still learning to comprehend. And consider that we're part of it, briefly conscious arrangements of atoms capable of looking outward and understanding what we see, building telescopes to peer across billions of years, developing mathematics to describe what should happen and comparing it to what does happen, slowly but steadily expanding our knowledge of the cosmos we inhabit. Thanks for exploring this cosmic mystery with me. Until next time, wherever and whenever you are in this vast, strange universe, keep looking up and keep wondering.